Thank you. Thanks for having me here. So I'm Sumanth, a researcher at DeepMind, at Google DeepMind, and I'll talk about some work we did recently on a watermarking technique for large language models. And if you go to gemini.google.com and get a response from there, that is actually watermarked with some of what I'll describe today. So to motivate the work, so why is tagging AI-generated content useful? So firstly, it's like it promotes transparency and the hygiene of the information ecosystem. So if you see a page on the web, you may want to know whether it was generated by an AI or it was human written or some mix of both happened and things of that sort. And the other forward-looking use case is if you're training the next generation of large AI models, you may want to filter some of this AI-generated data from the training corpus to make sure the models continue to do better and you have the next generation of models with greater capabilities and so on. And there's considerable evidence in literature that suggests that if you have AI models that are trained on AI generated data, these models collapse and continue to perform worse and things of that sort. And this is a nice paper if you haven't read it already. For numerous reasons, tagging AI generated content is nice and useful. And there are quite a few approaches for doing this. A common and popular one is logging and search or retrieval. Some people might call this retrieval, but the main idea is when a user interacts with your LLM that you have deployed, you save the response and then you either do an exact search or you use some sort of embeddings. And both of these options have their own drawbacks. With exact search, for example, you don't have any false positives, but you don't have any robustness to a few words being swapped out here or there, or a few punctuations changing and things of that sort. And on the other hand, if you're doing similarity search, as the number of entries in your log grow, you will see an increasing false rate, positive rate. And besides these two issues, the other bigger issue is also that you might have privacy concerns. So for example, say I have some private data in my model's response and that is logged. And if I let a third party search against it, there might be cross-user data leakage, which is a concern. Another popular technique that there's been a lot of progress on is also the use of AI classifiers for detecting AI-generated content. And the nice win here is that for these classifiers, you can actually hope to generalize to content that is not just from your LM, but also from other third parties. But then this again comes with a few catches. So one of them is you might see excellent performance on your hail.test set, but then when you're deploying this in the wild, you don't know how this will fare on out of distribution data, and it might fail in unexpected ways and have bad consequences and things of that sort. And this task of training classifiers might also get harder as the LLMs improve and they start behaving more like humans and things of that sort. And you might also hope that your AI content detection mechanism improves its performance as it sees more and more text from the source. But once again, you cannot guarantee this with AI classifiers. So to overcome some of these limitations, but with its own limitations again, we look at text watermarking. So with text watermarking, at least when we were thinking of deploying it at Google, the main desiderata that we were looking at was we wanted to have the best detectability possible. We wanted to make sure that when we watermark, we are not actually affecting the user experience either via quality or latency. But at the same time, we also want the watermark to be at least robust to a few minor perturbations. So say someone leaves out the last line from a Gemini generated essay, you still want to be able to tell that it was Gemini generated and not lose all of the watermark. During generation and detection, we want the whole process to be lightweight. And during detection, we don't want to assume access to the LLM weights or to the user prompt and things of that sort for obvious reasons. You may not want to share your proprietary LLM weights, or you might not want to leak user prompt data and things of that sort. These desired properties, I'll describe a method that attempts at getting at all of these. We call the SynthID-Text. So the first step to set the scene is, let's think about text generation from a language model. So the language model is prompted with, for example, in this instance, my favorite tropical fruit is, and let's say it assigns some probabilities to these 4 fruits: mango, lychee, papaya, and durian. So there's a 50% chance you get a mango, 30% chance you get a lychee, and so on. And you run your pseudo-random sampler in Python over these probabilities, and you end up with mango, for example. So now it is at this point that we introduce the watermark. And the way the watermark works is you have a held out watermarking key. So there's a key that is private to Google DeepMind for the watermark we have deployed. And you look at some recent context. So this is again a hyperparameter that you can configure based on what you want. So for example, here, let's say the hyperparameter is you look at the most recent trigram. So you take the most recent trigram, you take the watermarking key, and you choose a token from your vocabulary, and then you run it through your favorite hash function. And this hash function will assign, say, a 1 or a 0 to the word mango. And then it assigns a 0 to the word lychee, and so on and so forth. You do this with all the tokens in your vocabulary. So this is stage 1. So here you have a set of 1s and 0s assigned to each token in your vocabulary. And this changes with the key and also changes with the context. So if you had a different context, these 4 fruits would have gotten different scores. But with this context and with this key, this is what we get. So given that we have these scores, the next step is to sample not 1, but 2 tokens from this distribution. Instead of sampling just once, when we earlier had mango, we sample twice. So the first time we get lychee, and the second time we get mango. And we look up the scores for these 2 fruits in this table. And lychee scored a 0, mango scored a 1. 1 is greater than 0, so mango is the winner of this simple tournament. And then we return mango to the user. And this process is run at every step during the generation from the LLM. And as you can see, you're not actually doing another forward pass through the LLM or anything expensive. It's quite straightforward, and you're just like sampling twice from the same distribution. And one nice thing that we can show is in expected, if you had the G functions as a uniform distribution over all possible assignments of 1s and 0s, then you can look at the expectation of the watermark distribution for each of these instantiations. And the expectation of the watermark function is actually you can show that it is the language model distribution itself. So in that sense, you can think of watermarking as behaving like a pseudo-random sampler. So in Python, you get a distribution, you use a seed, and you get a choice from this distribution. And here, in some ways, you're doing the same thing. So you have this watermarking key and context, and you have this distribution, and you get a token from it. In expectation, you're also preserving the language model. So this implies that you're not actually breaking the language model and are preserving the underlying quality of the model. Here in this decoding process, we always choose the winner. So we are biasing the distribution of 1s and 0s towards having more 1s than 0s. And this is what we'll use during decoding, during detection. So somebody gives me a piece of text about mangoes. And what my first step is to chunk them into 4 grams and then start scoring them. So I score this first 4 gram into, this first 4 gram maps to 1. The second 4 gram maps to 0. The third 4 gram maps to 1, and so on. You run the whole sequence. And then if you have many more 1s than 0s, you say that there's a watermark that is detected. If you have equally many 1s and 0s, it's likely that the text was not watermarked. You can run a statistical test and get a p-value or some other interpretable metric as well. The paper has a few choices that we try out, and also ways to improve this detection strategy that I just outlined here. And one thing that we can also observe is the higher the entropy in your model, or the more diverse responses it can generate, the more ones you should expect to see. And this means that you get much better detectability. So as a corner case, let's say your model could only produce 1 piece of text, the exact same piece, then you don't actually have a choice at every step. So the watermarking is basically a no-op, and you don't actually get much watermarking there. So, okay, so this is like the most simple instantiation of the algorithm. Let's say we want to increase the detectability. So if you ask somebody working in deep learning what do you do to improve performance, the answer is add more layers. So this is exactly what we'll do. So instead of using a single cryptographic hash, we use many such hashes. So we get many such scores per token. And then instead of having a single round of the tournament, we have many such rounds. So instead of starting with 2 tokens at the first step, we sample 8 tokens. So here's an example with 3 layers of the tournament. Instead of starting with 2 tokens, we start with 8. And then we have this, we split them randomly pairwise and run the tournament. And then we do this over and over again. And the hash functions are chosen so that they're independent from each other. So there's no correlation. And then once again, you can show the same property as before, that in expectation over these families of hash functions, we recover the underlying language model. But then on the other side, on one side, we have preserved the quality, but on the other side, we have actually managed to get a lot more signal out of this watermarking process. Why? Because earlier we just had one observable, but now we have many observables. So if you think about watermarking in the sense of along the lines of coin tosses, now you have multiple biased coin tosses for every single token that you're generating. So let's say you have 100 tokens. So like if you have 10 layers of the tournament, now you have 1,000 biased coin tosses. Whereas earlier for the single layer setup, you had 100 biased coin tosses. So detecting 1,000 biased coin, telling whether a coin is biased with 1,000 biased coin tosses is much easier than with 100, and we see this effect pop up. So you see that the watermarking detection rate goes up as you increase the number of tournament layers. As we add more layers, we get better detectability, mainly because of the statistical power of more observables. But then there's not like really infinite free lunch here. So if you read through the paper, you see diminishing returns, and depending on the detector, your performance might even get worse with more layers. But I will skip those detectors. Instead of just counting the number of ones, you can go a step further and use some information about the underlying entropy available to you to design tests that consider both the watermark distribution of ones and zeros and the unwatermarked distribution, and do sort of a Bayesian statistics style check, and then you get improved performance because of that. So I leave all of those details because the talk is only 25 minutes. So this is at the level of a single token. But what we want to also do is preserve the quality across, like, say, for example, a full sequence. So for this, we use a simple heuristic. So for example, if you keep a store of all the hashes of n-grams that you previously saw. So for example, let's say here there was the trigram, which was fruit is mango, and then you watermark because. And then in the passage, the fruit is mango appeared again. But this time, you actually generate a token without watermarking. And what this means is this again preserves all of the guarantees as before, that in expectation over keys and things like that, expectation over G functions, you preserve the distribution of outputs from the LLM at the sequence level. There's other literature that also explores similar ideas, so feel free to have a look at those as well. One thing to again note is like this weakens the watermark because you're not watermarking a few tokens, and if a user is cropping pieces of text, you might not know when the user watermarked things and when they didn't, and this might lead to a bit of weaker watermarking. But this is a trade-off you have to make if you want to preserve the quality. So I spoke about non-distortionary tournaments and preserving the LLM distribution. So if you didn't actually care much about preserving the LLM distribution, we also offer an option where you can trade off some of the quality for much better, much stronger watermarking. One easy way to increase the strength of the watermark, but give up a bit of quality, is to increase the width of the tournament. So earlier we had two players per node in the tournament, but if you increase to 3 players, for example, you lose the guarantee that we had earlier, that in expectation over keys you recover the language model. But so you've slightly distorted the model. You no longer have the same guarantees, but then you have increased the watermark because you have a higher chance of picking a token with 1 because you have 3 players participating. But then why is this not such a great idea? So if you don't do the multi-layering, but you say have a single layer, but you increase the width to infinity, then if you look at the distributions, what you actually get is that the watermark distribution becomes a uniform distribution over the set of tokens which has support under the LLM. And a set of uniform tokens, uniform distribution of the vocabulary would essentially give you garbage, so that is not a good idea. Moving on from describing the method and a few key theoretical results, like let's see if the evaluations hold up to the claims I made. So the first is we compare the detectability of our approach with a couple of the most popular watermarking methods out there. So there is the watermarking method based on the Gumbel trick, which is also non-distortionary, and you can have similar guarantees on quality similar to our method. So we swap out the tournament sampling with Gumbel trick and then use the proposed detectors from literature, and we see that the tournament offers a improvement, a visible improvement here, and the improvement depends on the underlying entropy. In some settings, they both converge to similar performance, but I'll let you go through the paper for the full set of results. If you think watermarking is very critical and you are okay to take a bit of a quality hit, in this setting, we compare with the work from University of Maryland, which got the best paper at ICML last year. And here again, we show that we provide a better trade-off when trading off quality for detectability. So lower on the x-axis is better quality, and then we see that we have a better Pareto front end. Now we'll focus on a few more quality results, and primarily in the non-distortionary setting, because that is what we use in production. On the left is a set of results on some standard benchmarks for the Gemma 7b pre-trained model. We see that between the watermarked and unwatermarked model, there's no statistically significant differences. On the right, there's a set of results that correspond to the Gemma 7b instruction tune model. It's like a model with instruction tuning and RLHF and SFT and things of that sort that is trained to follow instructions. So this model is prompted with questions from the explain like I'm5 data set. And then this is sent to humans for rating. And based on the human ratings, we again see that there is no statistically significant preference for one model or another. Both the watermarking and the unwatermarked model are equally preferred within the error bars. And lastly, the most interesting part, which I think is critical, is we had all of these academic experiments and theoretical analysis around our work, and then came the time to put this into production. So at some point last year, a bunch of traffic from the Gemini web app was routed to a watermarked version of Gemini, and some of it was routed to an unwatermarked version of Gemini. And we looked at how users interacted and behaved with both the models, and we saw virtually no difference between their preferences and their behaviors across both of these models, indicating that we are not negatively impacting user performance. So while there is no impact on quality as indicated by these numerous results I shared, one thing to be mindful of is watermarking does impact the diversity of generations. If you're working with non-distortionary watermarks, we find that like SynthID offers a better trade-off. It preserves more of the underlying diversity when you apply the watermark compared to some other watermarks like the Gumbel trick. This is a plot showing the self-blue between multiple responses from the model for the same prompt. Higher your self-blue is, the more the overlap is, and you want to be as much to the left as possible. So I covered a few of the desired data. There's one last piece that I left behind. One of the last pieces that I left behind was the impact on latency. So if you want to put this into production, you don't want the user to be waiting for significantly longer than they would otherwise for a response. And we see that this is what happens. So the increase in latency for Gemma 7b for an unwatermarked versus unwatermarked model is around 0.5%. And as you scale up the model, this relative change is going to shrink further because the cost of watermarking does not go up. One other crucial piece to solving this whole puzzle was the compatibility with speculative decoding. So speculative decoding is very often used in production across companies. And then the main thing it achieves is it gets you the response from the LLM faster. And the main idea behind it is you have a draft of the response from a smaller model, and then you can do a batch forward pass through a bigger model. And then the bigger model gives you probabilities for this whole sequence of tokens. And based on that, you can accept or reject. And this gives you considerable speed ups. And there are two ways to blend in watermarking with speculative decoding. I won't go into the details. I'll touch upon this at a very high level. So there is one method which preserves the watermarking, but you can show through Jensen's inequality that you will lose some of the benefits from speculative decoding. So you will have slightly slower inference, which if that is a bottleneck for you in production, you can choose the other version, for which we have some results in the paper as well. So this version weakens the watermark, but preserves all of the benefits of speculative sampling. There's a way to blend in watermark with speculative sampling while preserving the latency benefits and the quality and all of the things I spoke about before. So now you might have the question, how does this watermark behave? Say I delete a punctuation, or just I say change 2% of the words or something. So the watermarks can tolerate quite a few perturbations. So for example, so here we've deleted 20 to 50% of the words, and you still see that the watermark persists, and you just need slightly longer text. But on the other hand, if you're doing like a thorough paraphrase, so for example, here we paraphrase responses from a Gemini 7b model with a Gemini Ultra. So the responses look nothing like before. The meaning sometimes changes, and the quality also changes quite a bit. In this setting, actually, we need significantly longer pieces of text, up to 3 orders of magnitude longer than we did if we had unmodified text. So there are ways to weaken the watermark, but you might end up changing the meaning. And the watermark is not absolutely brittle. You can change a few words here and there, and the watermark will still persist. One thing, as I mentioned before, is you can increase the robustness quite a bit, but this might come at the cost of quality. So obvious ways to increase the robustness would be to make the watermark distortionary at the token level, or remove the sequence level interventions we had to make the watermark non-distortionary, or you can shrink the context length and things of that sort. Again, that is a design choice you have as a person deploying the watermark. So I also touched upon one of the weaknesses of classifier earlier, that you don't know how they're going to behave on out of distribution text. So here we compare the performance of binoculars and SynthID on text on responses in various languages. So with binoculars, the underlying model had not seen text in a few of these languages, and it fails on them when you generate text from them. When you generate text in these languages, the detector is not able to generalize. But if you have a watermarked LLM, it kind of works across languages. And the other point I had also mentioned was about this monotonic trend of the detection getting better and better as you have more text. So with classifiers, you don't see the trend, but with watermarking tools, you often tend to see the trend that the performance gets stronger as you have increasing amounts of text, because you have more observables and you get more statistical power as a consequence. We went through a bunch of results, and what does this mean for looking forward? So one of the main takeaways from our work was that it is possible to deploy quality preserving, latency preserving watermarks in production systems. And hopefully there'll be wider adoption of watermarks across the board, and there'll be increased coordination, and with this, the hygiene of the web ecosystem will improve. The other point is we haven't solved all of the challenges here. These watermarks remain vulnerable to scrubbing and spoofing, as I showed with the paraphrase attack. There's also room for improved accuracy in low entropy settings. And there's also questions of like whether there can be entirely novel approaches of watermarking at the level of semantics, for example, where you can provide similar guarantees on quality, maybe get it into production one day. So that's an interesting direction as well. I also touched upon briefly on complementary tools that exist and how they all have their own drawbacks. Watermarking also comes with its own drawbacks. So a practical thing to do that could serve the community in the immediate future would be to look at how combinations of these tools will be useful and work and can be utilized in practice. And lastly, as we're all aware, like there have been some amazing models in the open as well. How do you get watermarking to work for these open models as well? Because the watermarking I presented is entirely voluntary, and it's something you turn on if you're a person deploying the language model. So how do you make the adoption of watermarking for open models more widespread? So that's an open question, and I think there's been some progress there, but that's an area to still continue working on. With that, I would like to thank this amazing set of collaborators without whom this work would have not been possible. There's a long list here, and there's many others at Google and DeepMind who were incredibly helpful in helping us get the open source, the paper, and also the system in production out. So I'd like to thank them all. And with that, I'm open for questions.
So I have a question. I'm confused. What problem are we solving with watermarking? So you watermark all the content that is produced by Gemini. Now I can
Yes.
tell whether this piece of content is produced by Gemini. That's what I can do, right? I can take your Gemini output, give it to Claude, and then come back to you. Your watermark will not work because I distorted the distribution completely. And what problem are we solving with water? Who are we trying to prove that this content is actually produced by Gemini?
So let's not even think about the adversarial case, right? So for example, say, I don't think I can take names in a public forum, but say you're a major LLM provider and you feel like, yeah, so like we're talking about the model collapse problem, for example, right? And then you don't even care about the adversarial user. You might care about the regular user, and like people are writing blogs on the internet, people are writing news articles with your LLMs, but you still want to keep improving your LLMs. But if a majority of the web is filled with content from your LLMs, then how do you address that question? And if you think about like a massive company, it might not even be possible to have a centralized log, right? Like you might have 60 different products, and you
Yes.
need coordination and stuff. And that's one of the problems. And then there's also maybe Claude will one day watermark too, and then it becomes a little harder and people are discouraged. Maybe they're not keen enough to spin up their own llama. So I don't think we'll solve the problem with this one single bullet, but maybe like a set of tools.
It's an idea. It's a good idea to think about. Yeah.
I have a follow-up question kind of like related to what Sophia is saying. I mean, it kind of feels to me that right now the current system is very much on the hands on the LLM provider, right? You decide if you want to enable the watermarking or not, and then you could even decide if you want to enable these publicly for others to check, a piece of text to see if it was generated using your model, right? So that will allow you to have some form of attribution to the services you're providing. Well, I think Sophia's point is actually really valuable because the generation of text, it doesn't come purely from the model itself, but the model was prompted, right? And so as part of the prompting, could you see, Sumanth, an expansion to the watermarking that includes the whole prompting dialogue that went from the user to the LLM and then linking that to a particular session for like the attribution of like, hey, okay, the LLM generated the output, but it was in response to a content that was enforced by me. And that part, must be unique to my interaction with the LLM. So someone, if they generate the same prompt, a slight different response will come, right? And so then you can have both attribution to the model as well as the user that used the model, right? It's like, is there any point in that expansion
Yeah, I
to
think it's
enable this?
possible to some extent, in the sense like people are looking at multi-bit watermarking. You can also extend our work to multi-bit watermarking, so you can encode more than just the single keys. You can embed a watermark with many keys, and that key could be like a hash of the prompt you gave the model or something of that sort. But I think it's a tricky space in the sense like, I don't know if there's surveillance risks and risks of other sorts, which could be problematic as well. So I feel like answering most of these questions is above my pay grade.
Okay, but now it's interesting that, I mean, I think it's feasible and it could serve a particular use case if needed. That was the question.
I'd like to just ask kind of a clarifying technical question because I want to understand what it's doing a little bit better. I had some uncertainty. So as I understood what you were saying, the LLM generates a logit distribution. You sample Monte Carlo sample from that to get 2 tokens, and then you use a pseudo-random number generator that's conditioned on the previous 3 tokens to decide which of those 2 tokens you're going to include in the output. Was that the correct understanding, or?
It was almost correct in the sense that we do. But there's one missing piece, is that like we use the pseudo-random number generator to score each of the tokens and then pick the highest scoring one. So we don't directly make the choice; we score them first.
Okay, so is it like you're feeding a pseudo-random number generator is conditioned on the previous 3 tokens and the generated token?
And the 2 generated tokens in this example. So the pseudo-random number generator is conditioned on your key. This tropical fruit is a piece of text, and at one point lychee, and then the next point mango. So you run this twice.
Okay, so you run it. You feed tropical fruit is lychee into your G function, your thing, your random function, and it puts out a 0, and that's a random 0.
Yes.
And then tropical fruit is mango, and that's a random 1. And those 0 and 1s are uniformly distributed, conditioned on the previous tokens. Is that right? Or
so that is deterministic, right? So if you fix the key, it is deterministic. But if you say there's a distribution of uniform keys, then there's a uniform distribution of 0s and 1s for each of these tokens.
Okay, well, let's see. It sounds like you said 2 things at once. The 0 and 1 on lychee and mango is you're saying it is deterministic on, so if I go tropical fruit is mango, I will always get out a 1?
If you have the key as the fixed one, like say your key is 1, if you take key as the 1, key 1 combined with tropical fruit is mango, you'll always get a 1.
Yeah, the key's going to stay constant though through this whole thing, right?
Yeah. So then you always get a 1.
And then when you're actually doing the watermarking, how did you decide whether to pick the mango or the lychee?
Just the highest score.
The 0, 1 are the scores?
Yeah. So whichever of the 0 or 1 is higher, yeah.
Okay. And if they tie?
You pick randomly.
Okay, now I do see why that changes the G distribution a little bit. Okay, with my mental model, I couldn't see how that would change the the G distribution. And so in non-generated text, okay, this will cause there to be a higher percentage of ones once you do the testing, right? You do the GGGs on all combinations of 4 tokens, and you'd expect to get, essentially, if you're doing 1 bit here, you'd expect to get, very high probability of 1, right? Because I guess 50% of the time it's not going to be a tie, and you'll generate a
Yeah.
1, right? So so you'd expect 50% of the time, at least, you should have ones there. Actually, 5% of the time you should have ones, right?
Yeah, 75%. But the catch is most LLMs, including the ones in production, like say ChatGPT, Gemini, they go through RLHF, SFT, and they're not run at high temperatures. So you lose a ton of entropy. And what that means is like the distributions are very peaky. So very often you end up with the same token twice if you sample twice.
Right.
So if you look at the distribution of Gs, it's usually around 52, 53%. So like it's a coin toss with a very little bias, and not the 75%. If it was 75%, you would need like 20 tokens and you would get some amazing detection rates. But in practice, we see that like the entropy is quite low. And but if maybe one day people figure out how to do RLHF very well, preserving all of the underlying entropy of the pre-training models, then these watermarking technologies will like work amazingly well, right? You need like 10, 20 tokens to get like perfect detection, and then you can solve a lot more problems with this. So adding entropy to the underlying model is one way to make progress on this problem as well.
Right. Okay, good. Thank you. Now I think I understand it better.